Find somewhere comfortable, somewhere the weight of the day can finally be set down. You don't need to follow any of this closely. You don't need to remember a single thing. The words will arrive, and you can let them pass through you like water moving over smooth stone, gently, without effort, without any need to hold on. Tonight, we are going somewhere very small, smaller than anything you have ever seen or touched. We are going inside the atom, inside the nucleus at its center, to find out what lives there and what happens when that quiet interior finally lets go. It is a journey that begins in stillness. The nucleus of an atom has been sitting, patient and unhurried, for longer than the Earth has existed. It holds an enormous tension inside itself, a tension between two forces that have been locked in permanent, silent contest since the first moments of the universe. And somehow, in the middle of that tension, there is beauty. There is structure. There is the quiet architecture of matter itself. We will move through this slowly. There is no hurry tonight. The science is deep, and we will go into it gently, one layer at a time, the way you might lower yourself into warm water, not diving, just easing in, letting the depth come to you. So settle now. Let your shoulders fall. Let your hands grow heavy, and when you are ready, or even if you are not quite ready, let the words begin. To understand what fission is, you have to begin where fission begins, inside the nucleus, in a space so vanishingly small that the word small barely does it justice. The atom itself is already extraordinarily tiny. A single hydrogen atom is roughly 1/10 billionth of a meter across. If you were to line up 100 million of them side by side, they would stretch about 1 centimeter. And yet, the nucleus, the dense, compact core at the atom's heart, is smaller still. It is roughly 100,000 times smaller than the atom that contains it. If an atom were scaled up to the size of a football stadium, the nucleus at its center would be about the size of a marble sitting on the center spot. Inside that marble, everything is packed extraordinarily tight. The nucleus contains two kinds of particle, protons, which carry a positive electrical charge, and neutrons, which carry no charge at all. Together, they are called nucleons, the residents of the nucleus. In a hydrogen atom, there is only one proton and no neutrons. In a helium atom, there are 2 protons and 2 neutrons. As you move up through the elements, the nuclei grow heavier and more complex, adding protons and neutrons in combinations that are sometimes stable and sometimes not. And here is where the tension begins to build. Protons carry positive charge, and positive charges repel each other. This is the electromagnetic force at work, the same force that makes a magnet push another magnet away when you hold like poles together. Every proton inside a nucleus is simultaneously being pushed away from every other proton, and that repulsion does not diminish quickly. The electromagnetic force has what physicists call long range. It reaches across the full width of the nucleus, and in fact it reaches across any distance at all, growing weaker with distance but never quite disappearing. So why don't all nuclei simply fly apart? Why doesn't every proton immediately flee from its neighbors? Because there is another force, a much more powerful one. It is called the strong nuclear force, and it is, in a very real sense, the most powerful force in nature. At the distances found inside a nucleus, distances measured in femtometers, where 1 femtometer is 1/1,000,000th of a billionth of a meter, the strong force is roughly 100 times more powerful than the electromagnetic force. It acts between protons and neutrons alike, pulling them together regardless of charge, binding them into a coherent whole. But here is the crucial detail, the thing that sets the stage for everything that follows. The strong force has an extremely short range. It only operates effectively across distances comparable to the diameter of a proton or neutron, roughly 1 to 3 femtometers. It does not reach across the full width of a large nucleus. It only binds particles that are immediate neighbors. In a small nucleus, in helium, say, or carbon or oxygen, this is not a problem. Every nucleon is close enough to every other nucleon that the strong force can reach between them all. The nucleus is tightly bound, stable, coherent. But now imagine adding more and more protons. As a nucleus grows heavier, its width increases. A uranium nucleus with 92 protons and, depending on the isotope, between 146 neutrons has a diameter roughly 6 times larger than a helium nucleus. A proton sitting on one side of a uranium nucleus is too far away to feel the strong force from a proton on the opposite side, but it can still feel the electromagnetic repulsion from that distant proton, and from every other proton in between. This is the fundamental asymmetry that makes heavy nuclei unstable. The strong force binds locally between neighbors. The electromagnetic repulsion acts globally across the whole nucleus. As nuclei get heavier, the electromagnetic pressure builds and builds, while the strong force's ability to compensate grows more and more strained. The nucleus is, in a sense, holding itself together against an ever-increasing internal push. Neutrons help. Because neutrons feel the strong force but carry no charge, they contribute to the binding without adding to the repulsion. This is why heavy elements need proportionally more neutrons than light ones. They are acting as a kind of buffer, a structural support against the electromagnetic pressure. In carbon, the most stable isotope has 6 protons and 6 neutrons, an equal ratio. In uranium, the most common form has 92 protons and 146 neutrons. The nucleus needs 54 more neutrons than protons just to hold together at all. And even then, it is not entirely at peace. Uranium-235 is the isotope we will return to again and again in this story. Its nucleus contains 92 protons and 143 neutrons, a total of 235 nucleons packed into that marble-sized space. It is, by any measure, a heavy nucleus. And that particular combination, 92 protons, 143 neutrons, sits in a region of the periodic table where stability is genuinely marginal. Not unstable enough to fly apart on its own in an instant, but carrying a persistent internal strain that, given the right nudge, can be resolved in a very particular and very energetic way. There is a useful image for this state of affairs, and physicists have used it for decades: the liquid drop. A nucleus in many ways behaves like a tiny droplet of liquid. The nucleons are packed together much as molecules are packed in water, held close by short-range forces, able to move relative to one another, but not to escape easily. A small droplet of water is stable. Surface tension holds it in a neat sphere. But if you stretch a droplet, if you pull it into an elongated shape, the surface tension that tries to pull it back into a sphere has to compete with the forces pulling the two ends apart. Stretch it far enough, and the neck in the middle becomes too thin to hold, and the droplet splits into two. A heavy nucleus is a droplet that has already been stretched somewhat past the point of comfort. The electromagnetic repulsion is the force pulling the ends outward. The strong force is the surface tension trying to hold the sphere together. The nucleus sits in a kind of delicate equilibrium, not breaking, but not entirely at ease either. Uranium-235 has been in that state of quiet tension for an almost incomprehensible length of time. The uranium in the ground beneath you was forged in the violent death of stars that lived and died before our solar system existed. In supernovae, in collisions between neutron stars, in the most energetic events the universe produces. That uranium was incorporated into the dust cloud that became the Earth roughly 4.5 billion years ago. And since then, those nuclei have been sitting in the dark, holding their tension, patient and still, waiting for a neutron to arrive. That neutron is coming, but not quite yet. It is worth pausing here, before the physics becomes more intricate, to sit with the human beings who first understood what was happening inside those heavy nuclei. because the discovery of nuclear fission is not a clean, triumphant story. It is something quieter and more complicated, a story of brilliance, confusion, exile, and an injustice that the scientific community has spent decades slowly reckoning with. The year is 1938. The place is Berlin, specifically the Kaiser Wilhelm Institute for Chemistry, where two chemists, Otto Hahn and Fritz Strassmann, have been conducting a series of experiments that they find increasingly difficult to explain. The experiments began with a straightforward enough idea, or at least straightforward by the standards of nuclear physics in the 1930s. Enrico Fermi and his group in Rome had spent the middle years of the decade bombarding various elements with neutrons to see what would happen. When a nucleus absorbs a neutron, it sometimes becomes a heavier, radioactive version of itself, or it might transform into a neighboring element on the periodic table. Fermi had tried this with uranium and reported what he believed were new, heavier elements being produced, elements beyond uranium on the periodic table, which would later come to be called transuranic elements. Hahn and Strassmann were attempting to follow up on this work, to chemically identify and separate the products of neutron bombardment of uranium. They were meticulous experimenters. Hahn in particular was one of the finest radiochemists of his era. And in December of 1938, after months of careful work, they found something that, by their own account, they could barely bring themselves to believe. Among the products of their neutron-bombarded uranium, they found barium. Barium, an element with only 56 protons, compared to uranium's 92, not a heavier element than uranium, not even close to uranium on the periodic table. Something roughly half the size of uranium. This made no sense within the framework of nuclear physics as it was then understood. You might knock a small fragment off a nucleus, an alpha particle which is 2 protons and 2 neutrons, but that would only change the element slightly. You could not, according to the prevailing understanding, split a nucleus into 2 pieces of comparable size. It simply was not supposed to happen. Hahn's response to this finding is captured in a letter he wrote on the 19th of December 1938 to Lise Meitner. She was no longer in Berlin. She had fled to Sweden 6 months earlier in July, escaping the increasingly dangerous situation for Jewish scientists in Nazi Germany. She had worked alongside Hahn for 3 decades. She was, by any fair account, a full intellectual partner in the program of research that led to this discovery. And now she was in Stockholm, separated from the laboratory, separated from the work, reading a letter from her longtime colleague describing a result that he called, in his own words, frightful. Hahn wrote that the chemical evidence for barium was unmistakable. He and Strassmann had checked and rechecked, but he could not explain it. He asked Meitner, as a physicist, whether she could suggest some explanation that would make the result less impossible. What happened next is one of the most extraordinary moments in the history of science, and it happened not in a laboratory, but in a Swedish forest. Meitner's nephew, Otto Frisch, was also a physicist, and he had come to visit her over the Christmas holiday. Frisch was working in Copenhagen with Niels Bohr. He arrived at the small town of Kungälv, near Gothenburg, to find his aunt sitting with Hahn's letter, turning the problem over in her mind. They went for a walk, Meitner on skis, Frisch on foot, through a quiet winter landscape of snow and bare trees. And as they walked, they talked through the problem. What if the nucleus had not merely shed a fragment? What if it had actually split into 2 roughly equal pieces? What if that was what the barium was, one of the 2 halves of a divided uranium nucleus? They sat down on a log, according to Frisch's later recollection, and they began to calculate. Meitner had an extraordinary memory for nuclear data. She knew the masses of the relevant nuclei. She knew the binding energies involved, and as they worked through the numbers on whatever scraps of paper they had available, something remarkable emerged. The mass of the two product nuclei, barium, and the other fragment, which would be krypton, was slightly less than the mass of the original uranium nucleus plus the incoming neutron. There was a small but definite shortfall in mass, and Meitner knew exactly what that meant. It was energy released in the splitting. The amount she calculated was approximately 200 million electron volts, 200 mega electron volts per atom. To put that in perspective, a typical chemical reaction, like burning a carbon atom in coal or wood, releases an energy of a few electron volts. A single fission event releases roughly 100 million times more energy than a single combustion event. Not 100 times, not 1,000 times, 100 million times. They returned from their walk with the outlines of a theory. Frisch went back to Copenhagen, consulted with Bohr, and performed experiments to confirm that the nucleus had indeed split. He named the process after the biological term for cell division, fission. Meitner published the theoretical explanation alongside him. The paper appeared in the journal Nature in February of 1939. The world of physics absorbed the news with a speed that reflected how profoundly significant everyone understood it to be. Within weeks, laboratories across Europe and North America were confirming the result. Within months, the possibility of a chain reaction was being seriously discussed. Within years, a very few years, that chain reaction would be achieved and the world would be changed in ways both terrible and, eventually, extraordinary. But here is the quiet injustice at the center of this story. In 1944, the Nobel Prize in Chemistry was awarded to Otto Hahn alone for the discovery of nuclear fission. Meitner received nothing. Strassmann received nothing. Frisch received nothing. The reasons are layered and uncomfortable. Hahn had done the experimental work in Berlin. Meitner's contribution was theoretical. The Nobel Committee at that time had a well-documented tendency to undervalue theoretical contributions relative to experimental ones, and an equally well-documented tendency to undervalue contributions by women. Meitner was both a theorist and a woman, and she was also a refugee, living in exile, without the institutional affiliation and visibility that might have pressed her case more forcefully. She was nominated for the Nobel Prize multiple times over the following decades. She never received it. She died in 1968 at the age of 89, widely celebrated in her later years. She had an element named after her, meitnerium, element 29, but never formally recognized by the institution that had recognized her colleague. There is something worth sitting with in that fact. The history of science is not a clean procession of discoveries and deserved rewards. It is a human history with all the bias and oversight and injustice that human histories contain. Meitner's contribution was real, and it was enormous. She understood, in a Swedish forest in December, what the nucleus was doing. She gave it a framework. She calculated the energy. And she did it while in exile, separated from her laboratory, reading a letter that described a result as frightful. That combination, the precision of her understanding and the difficulty of her circumstances, is something worth holding gently as we continue. We have arrived at the heart of the matter. If you are still awake, or half awake, let the following arrive like a slow narration of something very small and very old. A sequence of events that takes less than 1/millionth of a billionth of a second to complete, and yet contains within it a transformation of almost incomprehensible depth. A neutron is traveling through space, not a fast neutron. This one has been slowed down, its energy reduced until it is moving at a pace more in keeping with the thermal energy of its surroundings. We will come to why that matters in a moment. For now, picture it as a slow-moving particle, drifting without charge, invisible to the electromagnetic field that surrounds every proton in the uranium nucleus ahead of it. Because it carries no charge, the neutron does not feel the electromagnetic barrier that would repel a proton approaching from outside. It simply drifts in. And as it crosses the threshold of the nucleus, as it comes within range of the strong nuclear force, it is captured. The uranium-235 nucleus takes the neutron in and becomes, for one brief and turbulent moment, uranium-236. This is called the compound nucleus, and it is not a stable thing. The addition of one neutron has added not just mass but energy, the binding energy released when the neutron joins the nucleus, which cannot simply disappear but must go somewhere. It goes into the internal motion of the nucleus. The nucleons begin to move more vigorously, redistributing energy among themselves, the way molecules in a heated liquid move faster and more chaotically. And this is where the liquid drop model becomes most vivid. The uranium-236 compound nucleus begins to deform. It is no longer a neat sphere. It stretches, pulled into an elongated shape by the collective motion of its nucleons, and as it elongates, something important changes in the balance of forces within it. Recall that the strong force only operates across very short distances, only between immediate neighbors. As the nucleus stretches, the nucleons at the two ends move further apart, and the strong force between them weakens. But the electromagnetic repulsion between the protons does not weaken in the same way because it has longer reach. The 92 protons are still pushing against one another across the full length of the now elongated nucleus. So as the nucleus stretches, the strong force holding it together becomes relatively weaker at the center, and the electromagnetic force pushing the two ends apart remains strong. The nucleus develops what physicists describe as a neck, a narrowing region in the middle where the strong force is increasingly strained. The two lobes at either end grow larger. The nucleus looks, in this moment, something like a peanut or an hourglass, the material in the middle stretched to the point of failure. And then the neck breaks. The two lobes separate, repelled from each other by the electromagnetic force, now free from the strong force that can no longer reach across the gap between them. They fly apart at enormous speed, carrying most of the energy of the event as kinetic energy, the energy of their motion. They are called fission fragments, and they are themselves radioactive nuclei, typically something like barium and krypton, though the exact products vary from one fission event to another. The nucleus does not always split into the same two pieces. There is a range of possible outcomes, with some combinations more likely than others. Alongside the fission fragments, the event produces something else of enormous importance: free neutrons. On average, a uranium-235 fission event releases between 2 and 3 neutrons. These neutrons are emitted at high speed from the splitting nucleus, and they carry their own kinetic energy out into the surrounding material. There is also a release of gamma radiation, high-energy photons, the most energetic form of light, produced as the excited fission fragments shed their excess energy and settle toward more stable configurations. All of this happens in a time span so short that it is genuinely difficult to give it meaning. The entire process, from neutron capture to the separation of the fission fragments, takes on the order of a tenth of a femtosecond, roughly 10 to the power of minus 16 seconds. A femtosecond is already a millionth of a billionth of a second. We are talking about 100th of that. The event is, in any human sense, instantaneous. Now, where does the energy come from? This is perhaps the most important question in the whole story, and the answer requires us to think about what it means for nucleons to be bound together in a nucleus. When protons and neutrons join to form a nucleus, they do not simply sit alongside one another unchanged. The act of binding them together releases energy, the binding energy, the energy that would need to be supplied to pull them apart again. And here is the crucial point. The amount of binding energy released per nucleon, per individual proton or neutron, is not the same for all nuclei. It varies. For very light nuclei, like hydrogen or helium, the binding energy per nucleon is relatively low. As you move to heavier nuclei, the binding energy per nucleon rises. The nucleons are more tightly bound, more firmly held. It reaches a peak around iron and nickel, the elements sitting in the middle of the periodic table. These are the most tightly bound nuclei in existence. Beyond iron and nickel, as you continue to heavier elements, the binding energy per nucleon begins to decline again. The nucleons in very heavy nuclei, like uranium, are less tightly bound per particle than those in iron. This variation, plotted as a curve, is called the binding energy curve, and it is the key to understanding where fission's energy comes from. When uranium-235 fissions into two mid-sized nuclei, barium and krypton, say, those product nuclei sit closer to the peak of the binding energy curve than uranium did. Their nucleons are more tightly bound. The nucleons in the products have released more binding energy per nucleon than the nucleons in the original uranium. The difference between the binding energy of the products and the binding energy of the original nucleus is the energy that fission releases. That difference per fission event is approximately 200 mega-electron-volts. It sounds abstract, so let us translate it. 200 mega-electron-volts is the energy equivalent of a tiny fraction of mass. A mass defect, physicists call it. A shortfall between the mass of the original nucleus. The products weigh slightly less than what went in. That missing mass has not disappeared. It has become energy. The relationship between mass and energy is expressed in one of the most famous relationships in all of physics. Energy equals mass multiplied by the speed of light squared. The speed of light is roughly 300 million meters per second squared. That is an enormous number, about 90 quadrillion meters squared per second squared. So even a tiny amount of missing mass multiplied by that enormous factor becomes a vast release of energy. In a single fission event, the mass that disappears is roughly 1/5 of 1% of the total mass involved. That fraction seems negligible. And yet, it becomes 200 mega-electron-volts. Multiply that by the number of atoms in a small piece of uranium. There are roughly 2.5 times 10 to the power of 21 atoms in a single gram, and the total energy becomes extraordinary. One uranium fuel pellet, roughly the size of a thimble and weighing about 7 grams, contains enough fissile material to release the same amount of heat as burning approximately 1 ton of coal. Not a kilogram, a ton. The energy was always there, locked inside the nucleus, held in the binding between nucleons. Fission does not create energy from nothing. It releases energy that matter has been storing, patiently and silently, since the nucleus was first assembled in the heart of a dying star. The fission of a single uranium-235 nucleus is, in isolation, an event of no practical consequence. 200 mega-electron-volts is a significant amount of energy on the atomic scale. But on the human scale, it is nothing. A warmth too faint to measure, a sound too quiet to hear. The reason fission matters, the reason it can heat cities and power spacecraft and change the course of history, is what happens to those neutrons that the splitting nucleus releases. Each fission event produces, on average, between 2 and 3 free neutrons. Let us say 2.4, which is roughly the average for uranium-235. These neutrons travel outward from the splitting nucleus at high speed. They are fast neutrons carrying kinetic energies of around 1 to 2 mega-electron-volts each. And if the surrounding material contains more uranium-235, some of those neutrons will encounter further uranium nuclei. If they are absorbed, those nuclei will fission in turn, releasing their own neutrons, which will go on to trigger further fissions, which will release more neutrons still. This is the chain reaction. One event becomes 2, 2 become 4, 4 become 8, and so on, each generation of fissions producing more neutrons than the last. The mathematics of this doubling is exponential, and exponential growth is one of those things the human mind finds genuinely difficult to feel the scale of. 20 doublings takes you from 1 to roughly 1,000,000. 40 doublings takes you from 1 to roughly 1,000,000,000,000. In a very small fraction of a second, an exponential chain reaction in a sufficient quantity of uranium can involve an almost incomprehensible number of individual fission events. But whether the chain reaction actually sustains itself, whether each generation of neutrons actually produces at least as many fissions as the previous generation, depends on a crucial competition between two things: the probability that a given neutron will find the uranium-235 nucleus to split, and the probability that it will escape from the material before doing so. In a very small piece of uranium, most neutrons escape. The piece is small, and the neutrons are fast and directional. Most of them reach the surface and fly out into the surrounding air before they have a chance to encounter another nucleus. Cat. In a larger piece of uranium, fewer neutrons escape. The ratio of volume to surface area is more favorable. There is more material for the neutrons to travel through before they reach the surface. At some particular size and density, the chain reaction becomes exactly self-sustaining. Each fission produces, on average, exactly one new fission. The reaction holds steady. This threshold is called the critical mass. The critical mass of uranium-235 is not a single fixed number. It depends on the geometry of the material, its density, and what surrounds it. A sphere is the most efficient shape because it minimizes surface area relative to volume. Surrounding the uranium with a material that reflects neutrons back inward. A neutron reflector reduces the critical mass further. For pure weapons-grade uranium-235, the bare critical mass is roughly 52 kilograms, formed into a sphere about 17 centimeters across. For plutonium-239, another fissile material, it is considerably smaller. But there is a complication that Hahn and Strassman's original experiments already hinted at, and which Niels Bohr helped clarify in early 1939. The fast neutrons released by fission are not actually very efficient at triggering further fissions in uranium-235. They move too quickly. A fast neutron passing close to a uranium-235 nucleus has only a relatively small chance of being absorbed. It is, in a sense, moving too fast to interact effectively. It passes through the vicinity of the nucleus before the nucleus has time to capture it. Slow neutrons, neutrons that have been reduced to thermal energies, meaning they are moving at speeds comparable to the thermal motion of atoms at room temperature, are far more likely to be captured by uranium-235. The slower a neutron moves, the more time it spends in the vicinity of each nucleus it passes, and the greater the probability of absorption. The cross-section for capture, a measure physicists use for the effective target area a nucleus presents to an incoming particle, is many times larger for slow neutrons than for fast ones. This is where moderators come in. A moderator is a material that slows fast neutrons down without absorbing too many of them. The most effective moderators are materials whose atoms are light, close in mass to the neutron itself, because when a neutron collides with a light atom, it transfers a significant fraction of its kinetic energy in the collision, the way a billiard ball transfers energy to another ball of similar mass. A neutron colliding with a hydrogen atom, which is almost exactly the same mass as a neutron, can transfer nearly all its kinetic energy in a single collision. Water is an excellent moderator for this reason. It is full of hydrogen atoms. So is heavy water, which uses a heavier isotope of hydrogen called deuterium. Graphite, pure carbon, is also an effective moderator, not quite as efficient per collision as hydrogen, but it absorbs fewer neutrons, which makes it attractive for certain reactor designs. Enrico Fermi understood all of this by late 1942. He had been working in the United States since 1938, having left Italy after the Nobel Prize ceremony in Stockholm. He used the occasion to keep going west, not returning to fascist Italy. By late 1942, he was in Chicago, leading a team that was attempting to build the world's first artificial nuclear reactor. The location they chose was, by any measure, an unusual one. Beneath the west stands of Stagg Field, a disused university sports stadium at the University of Chicago, Fermi and his team assembled a structure they called Chicago Pile 1. It was exactly what the name suggested, a pile of material, specifically a careful arrangement of graphite blocks interspersed with lumps of uranium metal and uranium oxide. The graphite served as the moderator, slowing the fast neutrons released by fission down to thermal speeds. The pile was roughly ellipsoidal in shape, about 6 meters across and 5 meters tall. It contained about 49 tons of uranium in various forms and 385 tons of graphite. Running through it at various heights were control rods, long rods made of cadmium, a material that absorbs neutrons with exceptional efficiency. By inserting the cadmium rods into the pile, you could soak up the neutrons and suppress the chain reaction. By withdrawing them, you allowed more neutrons to circulate freely. On the 2nd of December 1942, Fermi and his team began withdrawing the control rods, one by one, in small increments, monitoring the neutron count with detectors as they went. The count rose with each increment. At 3025 in the afternoon, Fermi called for the final rod to be withdrawn to a calculated position. The neutron count rose and kept rising and did not level off. The reaction was self-sustaining. For 28 minutes, the pile produced a controlled, steady chain reaction, a few hundred watts of power, enough to run a handful of light bulbs. Fermi's colleague Herbert Anderson later recalled that when it became clear the reaction was self-sustaining, there was a moment of quiet. Then, a bottle of Chianti was produced from somewhere, and paper cups were passed around. The celebration was muted, because everyone in that cold basement knew what they had done and what it meant for the war that was still being fought across 2 oceans. One of those present, the physicist Arthur Compton, called James Conant in Washington with a brief coded message: "The Italian navigator has just landed in the New World." Conant asked, "How were the natives?" Compton replied, "Very friendly." The first controlled nuclear chain reaction in human history had taken place beneath the university sports stadium in a city in the American Midwest on a cold December afternoon. The world had changed, and most of the world did not yet know it. Chicago Pile 1 was not a power station. It produced no useful electricity, and it was never designed to. It was a proof of concept, a demonstration that a controlled, self-sustaining chain reaction was physically possible. The leap from that demonstration to a machine that could reliably and safely generate electricity for a city required a further layer of engineering: the controlled management of heat, the transfer of that heat to water and steam, and the conversion of steam into electrical current. It is worth tracing that path carefully, because it is a genuinely elegant piece of engineering, and understanding it reveals something important about how the immense energy of fission is brought down to the human scale. The central principle is straightforward. Fission releases energy primarily as the kinetic energy of the fission fragments, those 2 heavy nuclei flying apart from each other at high speed. In the dense material of a nuclear fuel rod, those fragments do not travel far. They collide almost immediately with neighboring atoms, and their kinetic energy is converted into heat. The fuel heats up. The temperature of the fuel rods rises. The question, then, is how to extract that heat usefully without letting the reactor overheat or the chain reaction run out of control. In the most widely used reactor design in the world, the pressurized water reactor, which powers the majority of nuclear power stations currently operating, the answer involves 2 separate loops of water kept completely isolated from each other and a steam turbine connected to a generator. The first loop is the primary circuit. Water in this loop flows directly through the reactor core, absorbing the heat produced by fission in the fuel rods. The water is kept under very high pressure, roughly 150 times atmospheric pressure, which raises its boiling point significantly above the normal 100 degrees Celsius. At this pressure, water can be heated to around 300 degrees Celsius without turning to steam. It remains liquid, which is important because liquid water is a far more effective carrier of heat than steam. This hot, pressurized water flows out of the reactor core and into a device called a steam generator, which is essentially a large heat exchanger, a structure where the hot primary circuit water flows on one side of a metal barrier and cooler secondary circuit water flows on the other. Heat passes through the barrier from the primary to the secondary circuit. The primary circuit water cools slightly and the secondary circuit water heats up and turns to steam. The secondary circuit steam is at high pressure and it is piped directly to a turbine, a large, multi-stage spinning machine not entirely different in principle from a jet engine that extracts kinetic energy from the flowing steam. The turbine is connected to a generator and the generator converts that rotational energy into electrical current. The steam, having given up much of its energy to the turbine, is then condensed back into liquid water, usually by passing it through a condenser cooled by water from a nearby river or sea or cooling tower, and returned to the steam generator to begin the cycle again. The two-circuit design serves an important purpose beyond simple efficiency. The primary circuit, which flows through the reactor core, becomes radioactive over time because neutrons from the fission reaction can activate atoms in the water and in the pipes. By keeping the primary and secondary circuits completely separate, the steam that drives the turbines is kept free of radioactivity, which simplifies the engineering of the turbine hall enormously. The reactor core itself is surrounded by a pressure vessel, a thick-walled steel container, typically about 20 centimeters thick, designed to withstand the high temperatures and pressures of the primary circuit and to contain any radioactive material in the event of a problem. Around the pressure vessel is a containment building, a structure of steel-reinforced concrete, typically about a meter thick, that forms the outer shell of the reactor building. This is the dome structure you see in photographs of nuclear power stations. It is designed to contain any release of radioactive material in the event of a serious accident, and it is one of the most robust structures in civilian engineering. Control of the reaction is achieved through the same principle Fermi used in Chicago, control rods. In a modern pressurized water reactor, the control rods are made of materials like hafnium or boron, containing alloys, materials that absorb neutrons very efficiently. They are arranged in bundles that can be inserted into or withdrawn from the reactor core by electric motors. When fully inserted, they absorb enough neutrons to shut the reaction down completely. When partially withdrawn, they allow the reaction to proceed at a controlled rate. There is also a subtler mechanism of control that operates automatically without any human intervention or mechanical movement. It is called the temperature coefficient of reactivity, and in a well-designed pressurized water reactor, it is negative. This means that if the reactor gets hotter than intended, if something causes the power to rise unexpectedly, the water in the primary circuit heats up, and hot water is a slightly less effective moderator than cooler water. Fewer neutrons are slowed to thermal speeds, fewer fissions occur, and the power naturally falls back toward the intended level. The reactor corrects itself. This self-limiting behavior is a fundamental safety feature built into the physics of the design, not into any mechanical system that could fail. Modern reactor designs take this principle considerably further. Many new designs include what engineers call passive safety systems, systems that respond to a loss of cooling, not by requiring pumps to activate or operators to intervene, but by using gravity and convection alone. Water tanks positioned above the reactor core can drain downward by gravity to flood the core if cooling is lost. The natural circulation of water, hot water rising, cooler water falling, can maintain cooling flow without any pumps at all. These systems are designed to keep the reactor safe for a period of days or even weeks without any external power or human action. The scale of nuclear power deployment that is possible when a society commits to it is illustrated vividly by France. After the oil price crisis of 1973, France made a deliberate national decision to shift its electricity generation to nuclear power. Not began construction on them, completed and connected them to the grid. By the 1990s, France was generating roughly 75% of its electricity from nuclear fission, the highest proportion of any country in the world. French electricity became among the cheapest and lowest carbon in Europe. The program was not without its critics, and the challenges of waste management and long-term safety are real and ongoing. But as a demonstration of what committed, systematic deployment of a technology can achieve, the French nuclear program has few parallels in the history of energy. The heat of a star tamed to turn a turbine, the tension inside a uranium nucleus, released in measured, deliberate increments, piped through 2 loops of water, converted first to steam, then to spinning metal, then to the electrical current that charges the phone on your bedside table or lights the lamp you turned off before you lay down tonight. Everything we have discussed so far, the careful assembly of moderators and fuel, the precise management of control rods, the engineering of cooling loops and containment structures, all of it might suggest that a nuclear chain reaction is something that can only be achieved through considerable human ingenuity and effort. But nature got there first, by about 1.7 billion years. In the West African country of Gabon, in a region called Oklo, there is a uranium deposit that has been mined commercially since the 1960s. In 1972, French scientists analyzing uranium ore from Oklo noticed something that should not have been there, or rather, something that should have been there but was not. The uranium in the ore had a slightly lower proportion of uranium-235 than natural uranium is supposed to have. Natural uranium, wherever you find it on Earth, consists of 2 main isotopes. Uranium-238, which makes up about 99.3% of natural uranium, and uranium-235, which makes up about 0.7%. These proportions are the same everywhere on Earth, because both isotopes were created in the same stellar events before our solar system formed, and they have been decaying at their respective rates ever since. But the uranium at Oklo had slightly less uranium-235 than it should. The missing uranium-235 had been used up, consumed. Subsequent analysis revealed something extraordinary. In at least 16 distinct locations within the Oklo deposit, the uranium ore had, approximately 1.7 billion years ago, achieved criticality and sustained a nuclear chain reaction, not for a moment, not for a day, but for somewhere between 100,000 and several 100,000 years. Nature had built a nuclear reactor. The question of how this was possible and why it cannot happen today with natural uranium requires us to think about the relative rates at which the 2 uranium isotopes decay. Uranium-235 and uranium-238 are both radioactive, but they decay at very different rates. Uranium-238 has a half-life, the time it takes for half of a given quantity to decay, of about 4.5 billion years, roughly equal to the age of the Earth. Uranium-235 has a much shorter half-life of about 700 million years. It decays about 6 times faster than uranium-238. This means that the further back in time you go, the higher the proportion of uranium-235 in natural uranium. Today it is 0.7%, too low to sustain a chain reaction in ordinary water, which is why modern power reactors use enriched uranium with the uranium-235 content raised to 3 or 4%. But 2 billion years ago, the proportion of uranium-235 in natural uranium was around 3%. 3%, comparable to the enriched fuel used in modern commercial reactors. At Oklo, 2 billion years ago, there was a rich vein of uranium ore with a uranium-235 content of around 3%, and there was groundwater. The water percolated through the porous rock, saturating the uranium deposit. It acted as a moderator, slowing the fast neutrons released by the spontaneous fission that always occurs at a low rate in uranium ore. With the neutrons slowed to thermal energies, and with uranium-235 at a concentration sufficient to sustain a chain reaction, the deposit went critical. The reaction generated heat. The water began to heat up, and eventually, in the hottest zones, it boiled away. When the water was gone, the moderating effect was lost. The fast neutrons released by fission were no longer being slowed to thermal speeds, and the chain reaction slowed and stopped. The uranium ore cooled. Eventually, groundwater flowed back in, saturating the deposit again. The reaction restarted. This cycle, heat, boil, cool, refill, restart, repeated over and over for hundreds of thousands of years. The natural reactor at Oklo was, in a sense, self-regulating in much the same way that a modern pressurized water reactor is self-regulating through its negative temperature coefficient. When it got too hot, it shut itself down. When it cooled, it started again. The temperatures reached in the reaction zones were relatively modest, perhaps 300 degrees Celsius at the hottest points, not dramatically different from the temperatures in a modern reactor core. The surrounding rock provided containment, and the waste products of the reaction, the fission fragments, the transmuted isotopes, remained largely in place, trapped in the mineral structure of the ore for the subsequent 1.7 billion years. This last point has been of considerable interest to scientists studying nuclear waste disposal. One of the central challenges of nuclear power is what to do with the spent fuel. These materials remain radioactive for thousands of years, and storing them safely for that duration is a genuine engineering and political challenge. The Oklo site offers a natural experiment in long-term waste containment. Most of the fission products generated in those ancient reactions have stayed put in the rock for nearly 2 billion years, migrating only millimeters to meters from where they were created. The geology of the site provided effective containment over timescales that dwarf anything human civilization has yet attempted. But perhaps the most philosophically intriguing aspect of the Oklo discovery is what the isotopic analysis of the ancient reactor zones tells us about the fundamental constants of nature. Nuclear reactions are exquisitely sensitive to the values of certain physical constants, numbers that appear in the equations of physics and that, as far as we can tell, are the same everywhere in the universe and at all times. One of these is the fine structure constant, a number that governs the strength of the electromagnetic interaction. If this constant had been even slightly different 2 billion years ago, the nuclear reactions at Oklo would have proceeded differently, and the isotopic ratios in the waste products would be different from what we observe today. Scientists have examined the Oklo waste products carefully and compared the observed isotope ratios to what the known physics predicts. The agreement is excellent. The fine structure constant, as best we can determine from Oklo's ancient waste, was the same 2 billion years ago as it is today, to within a few parts in 10 million. The laws of physics have not changed, at least not measurably, across nearly half the age of the universe. There is something very quiet and very deep in that finding. The rules that govern the nucleus, the same rules that Hahn and Meitner and Frisch worked out on paper in 1938 and 1939, have been operating unchanged since long before the Earth existed. They were operating in a patch of West African rock 2 billion years ago, running a nuclear reactor for hundreds of thousands of years, leaving traces that we can still read today. The image most people carry of nuclear fission is a large, steam-wreathed power station, or perhaps the more somber associations of the weapons that first demonstrated fission's destructive potential. But fission has a quieter life as well, a life of small, carefully controlled quantities of radioactive material sent out into the world to heal and to explore. Inside a nuclear reactor, the fission process produces not only heat and fast neutrons and gamma rays, but also a rich variety of radioactive isotopes, atoms whose nuclei have been left in unstable configurations, either as direct fission products or as the result of neutron capture by other materials placed inside the reactor specifically to be irradiated. These isotopes, produced in carefully managed quantities, are extracted from the reactor and shipped to hospitals and research centers around the world, where they serve as the basis of nuclear medicine. Iodine-131 is one of the oldest and most important of these medical isotopes. It was discovered in 1938, the same year as fission itself, and it has been in continuous medical use ever since. Iodine-131 is a radioactive form of iodine. It has 53 protons, like all iodine, but 78 neutrons instead of the 74 found in stable iodine. It decays with a half-life of about 8 days, emitting beta particles, fast electrons ejected from the nucleus as a neutron converts to a proton, and gamma rays. The medical utility of iodine-131 derives from a simple biological fact. The thyroid gland, which sits at the base of the throat, absorbs iodine preferentially from the bloodstream. It uses iodine to produce thyroid hormones, and it does not distinguish between stable iodine and radioactive iodine. When a patient with thyroid cancer or an overactive thyroid is given a carefully calculated dose of iodine-131, the thyroid gland absorbs it, and the radiation it emits destroys thyroid tissue from within. The treatment is targeted by biology itself. The body delivers the radioactive material to exactly the right place. Cobalt-60 is another reactor-produced isotope with profound medical applications. It is made by placing stable cobalt-59 inside a reactor, where it absorbs a neutron and becomes cobalt-60. Cobalt-60 decays with a half-life of about 5.3 years, emitting high-energy gamma rays. These gamma rays, focused into a beam and directed at a tumor, can deliver a lethal dose of radiation to cancer cells while sparing much of the surrounding healthy tissue. Cobalt-60 teletherapy machines, radiotherapy units using cobalt-60 as their source, have been used to treat cancer in hospitals around the world for decades, and they remain in use today, particularly in countries where more complex particle accelerator-based systems are not available. Beyond these two, reactors produce a wide range of other isotopes used in imaging, in therapy, and in research. Technetium-99 MF. The M stands for metastable, meaning it is a nucleus in a temporarily excited state, is perhaps the most widely used diagnostic isotope in the world. It is produced indirectly from reactor-made molybdenum-99, and it is used in tens of millions of medical imaging procedures every year. It emits gamma rays that can be detected outside the body, allowing doctors to image the function of the heart, lungs, kidneys, and bones in ways that X-rays cannot. These are not exotic applications. They happen in hospitals every day, in every country with a functioning healthcare system. The fission that lights a city also, in a quieter and more intimate way, helps a doctor see inside a patient's chest. But fission's reach extends much further than any hospital. It extends, in fact, beyond the solar system. The Voyager spacecraft were launched in 1977, two of them within weeks of each other, on trajectories that would take them on a grand tour of the outer solar system. Voyager 1 flew past Jupiter and Saturn. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to have visited the two outermost planets. Both spacecraft are still operating. Both are still sending data back to Earth. Voyager 1 crossed into interstellar space, the region beyond the influence of the Sun's solar wind, in 2012, and Voyager 2 followed in 2018. They are now the most distant human-made objects in existence, traveling through the space between the stars. They are powered by radioisotope thermoelectric generators, devices that convert the heat of radioactive decay into electricity. The Voyager RTGs use plutonium-238, a radioactive isotope produced in nuclear reactors. Plutonium-238 decays by emitting alpha particles, helium nuclei, and releasing heat. It has a half-life of about 87 years, which means it releases its heat slowly and steadily over a timescale suitable for a long space mission. The thermoelectric part of the generator uses a principle discovered in the 19th century when one end of certain materials is kept hot and the other end is kept cold. A small electrical current flows. In the Voyager RTGs, one side of the thermoelectric material is heated by the plutonium-238, and the other side faces the cold of space. The temperature difference drives a current. No moving parts, no pumps, no fuel to run out on any human timescale. Just the steady, patient decay of a radioactive nucleus, releasing heat, and the conversion of that temperature difference into electricity. The RTGs launched with the Voyager spacecraft in 1977 have now been operating for nearly 50 years. The power output has declined as the plutonium-238 decays, but both spacecraft are still generating enough electricity to operate some of their instruments. The data they are sending home, about the nature of interstellar space, about the boundary between the solar wind and the interstellar medium, is being received on Earth and analyzed by scientists today. The same physics that Meitner calculated in a Swedish forest in December 1938, the same relationship between mass and energy, the same understanding of nuclear binding and radioactive decay, now hums quietly aboard two small machines tumbling through interstellar space, more than 20 billion kilometers from the Sun. The development of small modular reactors, compact nuclear power plants designed to be manufactured in factories and deployed in smaller communities or remote locations, represents the next chapter in this story. These reactors, several of which are in advanced stages of development and regulatory approval in the United States, Canada, and the United Kingdom, use the same fission principles as their larger predecessors, but in a form that can be built more quickly, sited more flexibly, and operated with even more comprehensive passive safety features. Some designs are intended to provide power to remote communities currently dependent on diesel generators. Others are intended to produce the high-temperature heat needed for industrial processes like hydrogen production. And further out still, nuclear thermal propulsion, using a nuclear reactor to heat propellant to extreme temperatures and expel it to generate thrust, is being actively developed for future deep space missions. A nuclear thermal rocket can achieve roughly twice the propellant efficiency of the best chemical rocket engines. For a mission to Mars or to the outer planets, that difference is not marginal. It could reduce travel time significantly and open missions that would otherwise be impractical. The United States Defense Advanced Research Projects Agency awarded development contracts for a nuclear thermal propulsion demonstration in 2021, with testing planned for the mid-2020s. From a hospital ward in Manchester to the edge of the solar system, from a thyroid gland absorbing iodine to a spacecraft crossing into interstellar space, the applications of fission are not a single story but many stories, unfolding simultaneously across scales of distance and time that the mind can barely encompass. We have traveled a long way tonight, from the interior of a uranium nucleus, that dense, tense, patient marble of protons and neutrons, through the laboratories of Berlin and the forests of Sweden, through the basement of a Chicago stadium and the engineering halls where reactors were designed and built, through a patch of ancient rock in West Africa and outward, past the planets, into the space between stars. It is time now to let the journey slow, to let the ideas settle, the way sediment settles through still water, gently, without hurry, finding their natural resting place. Everything we have explored tonight connects back to one thing, the binding energy curve. That graph, the one that shows how tightly bound nucleons are in different nuclei, rising from hydrogen, peaking at iron and nickel, declining through the heavy elements toward uranium, is, in a sense, a map of the universe's preferences. A map of where matter would rather be. Heavy nuclei, sitting on the declining right side of that curve, carry more energy per nucleon than the mid-sized nuclei that fission produces. They are, in a meaningful physical sense, less settled than their products. Fission is not an explosion in the way we usually imagine explosions, something chaotic and destructive imposed from outside. It is, at a deeper level, simply matter, finding its way toward a more comfortable arrangement. The uranium nucleus fissions because doing so allows its nucleons to reach a state of lower energy, more tightly bound, closer to the stable middle of the curve where iron sits. The energy released is the difference between where the matter started and where it ends up. It is the energy of settling. There is something restful in that framing if you let it arrive slowly. The universe has preferences. It prefers certain configurations of matter over others. Iron is the universe's favorite element. In a sense, iron 56 sits at the peak of the binding energy curve, the most tightly bound nucleus that exists. Every process in nature that releases nuclear energy, fission of heavy elements, fusion of light, moves matter toward that peak. The universe is, very slowly and by many paths, working its way toward iron. And the force at the center of all of this, the strong nuclear force, deserves one more moment of quiet attention. We described it earlier as 100 times more powerful than electromagnetism at the distances inside a nucleus. But that description, accurate as it is, does not quite capture how strange and extraordinary this force is. The strong force operates across distances measured in femtometers. 1 femtometer is 10 to the power of minus 15 meters. The nucleus of an atom is a few femtometers across. The atom itself, the electron cloud that surrounds the nucleus, is roughly 100,000 times larger, measured in angstroms, where 1 angstrom is 10 to the power of minus 10 meters. The strong force is entirely confined to the nucleus. It does not reach into the atom, let alone into the space between atoms. It has no effect on chemistry. It has no effect on the way atoms bond to form molecules, the way molecules form solids and liquids, the way matter behaves at the scale of everyday experience. All of chemistry, all of biology, all of the physical world we inhabit and perceive, all of it is governed by electromagnetism and gravity, with the strong force locked away inside the nucleus, invisible, unfelt, doing its work in silence. And yet, through its limits, through the fact that it cannot reach across large nuclei, that it loses the contest with electromagnetic repulsion in atoms as heavy as uranium, it is responsible for fission. And fission is responsible for the electricity in your home, for the isotopes that diagnose cancer, for the power that carries Voyager through interstellar space, a force confined to a space smaller than a proton, operating in silence and invisibility, has shaped the world in ways that reach all the way to the edge of the known universe. The scale of the energy involved is worth resting with one more time. A single uranium fuel pellet, the size of a thimble, contains enough energy to equal roughly 1 ton of coal. A ton of coal is a significant physical object. It would fill a large wheelbarrow several times over. It would be heavy to lift. It would take up space in a room. The fuel pellet weighs about 7 grams. You could hold it between 2 fingers. And the mass lost in the fission of that pellet, the mass converted into the heat and radiation and kinetic energy of the fission fragments, is a fraction too small to weigh by any ordinary means. A few hundredths of a gram, a fraction of the pellet's mass. And yet, it becomes enough energy to heat a house for months. The mass is not destroyed. Nothing is destroyed in fission. The total amount of mass energy in the universe is conserved. It simply changes form. Mass becomes energy. The binding energy that nucleons carry, locked inside the nucleus since those atoms were forged in a dying star, is released as heat and light and radiation. It was always there. Fission does not create it, it only releases it. Think of the uranium in the ground beneath you, in the rock, in the soil, in the trace quantities dissolved in the water table. Every atom of uranium-238 in that rock has been sitting there for as long as the Earth has existed. Every uranium-235 atom, the ones that fission so readily, has been carrying its tension for 4 billion years, waiting for a slow neutron that, in nature, almost never comes. The strong force has been holding those nuclei together, patiently, silently, through the formation of the oceans and the emergence of life, and the slow drift of continents and the rise and fall of everything that has ever lived on this planet's surface. That is not a metaphor. It is literally true. The atoms in the ground are old beyond any scale that feels real, and they have been holding, all this time, an energy that we have only known how to access for the last 80 years or so. 80 years against 4 billion. We arrived very recently at the understanding that the ground beneath us is a storehouse of ancient stellar energy, released in the hearts of stars that died before the sun existed. Lise Meitner understood this, sitting in a Swedish forest in December, working out the numbers on a scrap of paper. Otto Frisch understood it as he walked beside her through the snow. Enrico Fermi understood it as he watched the neutron counters rise in the basement of a sports stadium in Chicago. The understanding arrived in a rush, in just a few years, after billions of years of that energy sitting quietly in the rock, waiting. And now it lights cities. It travels in the bloodstream to heal. It hums aboard spacecraft crossing the boundary into interstellar space. It runs, ancient and patient, in a patch of West African rock where it burned for hundreds of thousands of years before any creature existed that could have understood what it was doing. The universe is very old. The forces that govern it are very deep. And the energy locked inside the nucleus of a heavy atom is, in the most literal sense, a piece of stellar inheritance, a legacy from the stars that made the matter of which you and everything around you are composed. You are made of atoms forged in those same stellar furnaces. The calcium in your bones, the iron in your blood, the carbon in every molecule of every cell. All of it was assembled in the interior of stars that lived and died long before the Earth existed. You carry that history in every atom, and the atoms in the ground carry it too, along with their tension, their patience, their ancient stored energy. It is a long way from a uranium nucleus to a sleeping mind, but perhaps not so different in the end. Both are holding something. Both are, in their way, resting. The nucleus holds its binding energy, tight and quiet, patient across geological time. And you, whatever you are carrying tonight, whatever the day left behind, you can set it down now. The forces that hold the universe together are very old and very patient, and they do not require anything of you in this moment. The binding energy of the nucleus has been there for 4 billion years. It will be there tomorrow. The universe is not in a hurry. And so we leave it there. Somewhere behind you, the day is already distant. The atoms in the walls around you are holding, as they always have, their quiet tension. The strong force is doing its ancient work, in the dark, in the silence, in every grain of matter within reach of your sleeping breath. Let that be enough. Drift now, if you are ready. Sleep well.